So let me recall where we were getting at last time. So we are now interested in the scaling limit of random trees. Okay, so remember that Tn denotes a uniform, random, and rooted plane tree with n edges. Okay, and there are Catalan n many. Okay, just take one at random, and later we'll see that ln is labeling, but we'll come to that later. Okay, we were interested just in the scaling limit of the tree itself. And recall that you can code or describe Tn in terms of its contour or contour process. And this one I want to call it Cn. So maybe I use the notation Ctn, or maybe let me sum that up in Cn. So recall that the contour of a tree is, if you like, a random walk path of length 2n, where n is the number of edges again, and you know, it's the path that records the height of, say, a particle that travels along the tree in contour order. Okay, so here the contour process would be something like that. Okay, so that's Tn and Ctn. And as I said last time, so Cn is then a simple random walk, but conditioned on being non-negative all the way through, okay, and being equal to 0 at time 2n. Okay? It's just because from any such path, okay, from any path that has these two properties and you know, which take integer values and varies by +1 or -1 between these integer values, I can associate a tree. And how do I do that? So I didn't really mention that like last time, but if you want a nice picture to go from there to there, you should imagine that you glue the points that are facing each other below the curve. Okay, so if you identify the points that are located on all those red lines, what you will get is the tree that is located here. For instance, the edge that appears here corresponds exactly to the points that are identified on this side. Okay, so another way to say it is that, as we know, trees, you can view them as polygons that are glued in a certain way. So when you unfold the polygon, you are exactly creating these pairs of points identified like this. Okay. Okay. So don't think it's necessary to be too formal here, but so starting with any such path, you can obtain a tree. And so if you take a tree uniformly at random, it means that you have chosen uniformly at random such a path, and so it has to be you know, a simple random walk path conditioned on these two properties. Okay, and therefore, so it's natural to expect that Cn, when properly rescaled, and as I said last time, rescaled in a diffusive way, this converges in distribution as n goes to infinity to a limiting process, which I want to call E, and she's called the normalized Brownian excursion. And so I didn't mention that last time, but so the convergence in distribution, I want to consider it, so in distribution, in the set of continuous functions, say defined on 0, 1, together with the uniform norm. Okay? So, of course, this, you know, tacitly what I'm saying is that Cn, that's actually drawn here, you know, between integer values, you just interpolate it linearly and you obtain a continuous path. Okay? So, again, so I'm not going to give a full proof, I mean, even not a sketch actually. I'm just going to comment on this theorem and maybe, so for a proof, so there are actually several nice ways to prove this theorem. Okay, let me mention see the notes of the Buzios summer school. In 2010, so it's available on my web page, and it's published. It's also published in the AMS. Okay, and so these are lecture notes. Actually, so maybe I should have mentioned that right from the start. But so these Buzios summer school notes are written by Jean-François Le Gall and myself. Okay, there are also notes in which a proof of this theorem is not given, but that can be useful to you if you want to have complements on what I'm saying. So see also the Saint-Flour summer school notes. So for now they are only available on my web page, and they are actually not completed yet. Okay, but you can have a look at them. Okay, so again, I'm not going to prove this theorem, but I at least want to comment on it. So what is E? So again, it is a Brownian motion, Vt, but conditioned on B1 equals 0 and you know, Vt non-negative all over the interval, and this conditioning really does not make sense. However, one way to construct E is to take a path of a Brownian motion. Okay, so you take a path of a standard Brownian motion, and you look at the last time before 1 where this path was equal to 0. Okay, and call this point, for instance, G. And you look at the first point after 1 where the path is back to 0. Okay, so you let, so Bt is a standard Brownian motion, and let G be the supremum time less than 1 such that Bt is equal to 0, and D is the first time after 1 where Bt is equal to 0. And now what you want to do is you want to take the excursion of Brownian motion away from 0 on this interval. Okay, so this red path, and you want to rescale it in a diffusive way. Okay, so set, let's say, E tilde t to be equal to b at time g plus t times d minus g, and divided by square root of the length of this interval, and that's defined for 0 less than t less than 1. Okay, then E tilde is distributed as the the normalized Brownian excursion. Okay, so it's really so of course taking the excursion of Brownian motion that straddles 1 is just one of many ways of selecting an excursion of Brownian motion away from 0, and essentially if you have another natural selection procedure and rescale in this way, for instance, if you take the first excursion of Brownian motion, okay, so yeah, so sorry, so forget what I said. So it's you have to do it in a careful way, in fact. Okay, but the message is really you take an excursion of Brownian motion and you somehow condition it, you force it to have duration 1. Okay, and that's the process E. Maybe also some words about how you prove this theorem. Actually, this theorem can be seen as a consequence. So this theorem can be seen as an elaboration of maybe Donsker's invariance principle. Well, okay, so Donsker's invariance principle tells you that any centered random walk with a finite variance state distribution converges to Brownian motion after rescaling. Here, I'm not using this result in its full generality. I'm just applying it to simple random walk, if you like. Okay, so if I take S, a simple random walk on Z, and look at S at time nt divided by square root n, this converges in distribution to Brownian motion. Okay, you can, if you like, restrict the path to 0, 1 if you want to stay in the context of continuous functions of 0, 1, but otherwise you can take the topology of a uniform convergence of compacts, odd compacts. And the observation that you make is that away from 0, this conditioned walk Cn is absolutely continuous with respect to S, and well, with a density somehow that well, okay, let's say that is strictly positive, or that is bounded away from 0 as n goes to infinity. So what does this mean? It means that if you look at the path of your simple random walk with this conditioning, and let's assume that you can prove that at a small time, say epsilon times 2n, let's assume that you know that the walk is already sufficiently high in the positive numbers, something like bigger than square root 2n times some little eta. Then what happens is that the portion of the path that you are looking at here, so okay, again, away from 0. So you also have the times have to stay away from 0 and 1. But let's say you look at the portion of the path between 1 minus 2n epsilon and 2n epsilon. Then what you are looking at here is something that resembles very much, in fact, the path of simple random walk. Okay, it's when you are far away from 0, the conditioning is now something that that has a positive probability to happen. Okay, the conditioning by the fact that this path of random walk is positive is now something that is bounded away from 0. And of course, you have to account for the fact that you want to be back at 0 at time 1, but at least this is the idea. And the same, in fact, happens for the Brownian excursion. So the Brownian excursion, if you somehow, it has a so-called entrance law. You know what's the law of the Brownian excursion at time epsilon. And then the path of the Brownian excursion, at least up to a time which is very near 1, is something that is also absolutely continuous with respect to Brownian motion, at least so when you restrict it on an interval away from 0 and 1. Okay? So the idea is that at least when you are far away from the extremities of the interval, you can apply Donskers invariance principle. You know, it's just a non-singular conditioning on this theorem, and then somehow you have to prove that what's remaining in the initial and last segments is something that is, you know, it's a bit of the process that is not too big somehow. You have to prove the so-called tightness of this path, but I don't have time to do it in these lectures. Yes.
It works like naively. You want to say also to apply Donsker to say you take the excursion of a random walk and converge to the excursion. No, you take the mesh. And
you mean you take, for instance, the excursion of the random walk that goes above 1? So that would be true, of course. If you want to, if you take the excursion of, you know, so let's imagine that this is a path of random walk rescaled, okay, the simple random walk, and you take the excursion that goes across 1 like this. It will converge to the excursion that goes across 1 in the Brownian case. The only problem is that the path that you see here in the random walk setting has a random length. Okay, so somehow you want to condition this length to be exactly equal to 2n, and so there is a difficulty here. Okay, if you want to have the exact law that is here, you need to work a little more. It's you know, it's a bit the same thing in a very very much simpler setting, but so as Vincent said yesterday, the continuum processes have many symmetries that the discrete processes don't have. You know, for instance, the Brownian motion is conformally invariant. So you don't see that on random walks. And here it's a very simple expression of this fact. Okay.
So is E the same as Brownian bridge rerouted at the minimum?
Absolutely. Yeah. Okay. So, you know. In fact, I could spend 2 hours talking about this. There are really nice things. So, okay. So, another thing is that, as Vincent says, E is also Brownian bridge rerouted at its minimum. So, what does that mean? So, it's actually called a Vervat transform. So what does that mean? Well, at least I think we all have seen what a Brownian bridge is. It's a Brownian motion conditioned to be at 0 at time 1. And it's again a singular conditioning, but this one is not as bad as the conditioning for E. And there are in fact very concrete representations for this process. For instance, you can take Brownian motion and compensate it by a linear drift in order that it's equal to 0 at time 1. Okay, so you just subtract t times b1, and that has the same distribution as the Brownian bridge b. Okay, so okay, actually. Okay, and now you know, from the path properties of Brownian motion, you know that whenever it attains a minimum on a compact interval, well, actually a local minimum, it will attain it only once. Okay, so there is only one time where the overall minimum of this bit of Brownian, of this Brownian bridge is attained, and then you can exchange this left path before the minimum and the right path. So you just take this bit of the path and put it there. Okay. Okay. And now you obtain a new path, okay, which is a path defined on this interval, 0, 1. and this also has the law of the Brownian excursion. Okay, and actually, this can be turned into a, I mean, this fact can be used to also prove this theorem in a rather different way than the one that I've sketched here. And the idea that there is also a discrete analog to that. So the idea that is that Cn is also, okay, so it's also simple random walk conditioned on being, so here I have to be a little bit careful. So I want to condition it to be equal to -1 at time 2n plus 1 and rerouted at its minimum. Okay, so what does that mean? So I have a trajectory of a simple random walk, and I want it to be equal to -1 at time 2n plus 1. Okay, so maybe let me draw something maybe a little more interesting here. So I want it to be equal to -1 at time 2n plus 1, and then I shift everything at the, so actually now there are not only one minimum, so I want really to reroute it at its first minimum. Okay, the first time I attained the overall minimum of the path. And again, I want to exchange the part after and the part before. Okay, so in this case, I will obtain something like that. Okay, so you notice that here, you know, since I took a path of length 2n plus 1 rather than 2n, the path I obtain is also of length 2n plus 1, and it finishes at -1. Okay, so it's not quite the same as Cn, but you can see that almost by definition, before 2n, you are above 0. Okay, so it's really the restriction of the simple random walk on this time interval, and maybe restricted to 0 to n. Okay. So that if you can prove that the random walk with this conditioning converges after rescaling to the Brownian bridge, then it will show you that Cn, after rescaling, converges to this Vervat transform of the Brownian bridge. Okay, and okay, the convergence of simple random walk conditioned on that to Brownian bridge is, in fact, it goes along similar ideas than the one I've written there, but it's simpler. Something we can maybe discuss over office hours if you like. And well, actually, this fact, you know, of rerouting, it comes from a very general property of processes with exchangeable increments or cyclically exchangeable increments. So maybe a very nice reference for that is Pitman's Saint-Flour notes, which I definitely recommend that you have a look at if you haven't before. All right. Okay, so that's all I want to say about this theorem. And now let's look at what it implies at the level of trees. Okay. So now note that distances in Tn are simple functions or functionals of Cn. So namely, so let maybe V0, V1, V2, V2 and -1 be the contour exploration of Tn. Okay, so that means that Vi is the ith visited vertex in contour order. Okay. So again, this list is not. There are redundancies in this list. Okay, you visit every vertex as many times as its degrees. Okay, Now, note that the distance in Tn between Vi and Vj, well, first of all, maybe dTn between Vi and V0, by definition, it's Cn of I. Okay, it's just the height of Vi, so it's the distance to the root vertex. Okay, I didn't mention that, but that's the root vertex. Okay. Okay, so we know the distances to the root. Now, so maybe I need a little picture here. So now let's take, for instance, this tree and the contour process. Okay, I think that's it. And let's look, for instance, at the distance between this Vi and this Vj. Okay, so they are visited respectively at this time I and this time j. Okay. So the distance between Vi and Vj is equal to the sum of two lengths. You know, it's the path that goes from Vi up to the root, but stopped at the most recent common ancestor between Vi and Vj. Okay, this one I want to call it Vi min Vj. How do you recover that on the contour process? Well, you can see that when you travel from Vi to Vj, you visit only vertices of the subtree above Vi min Vj. Okay, and there will be one time between Vi and Vj where you actually visit a corner incident to this most recent common ancestor. Okay, so the height of Vi minus Vj is actually the smallest value of the contour process between I and j. Okay. Okay, so another way to say it is that the distance between Vi and Vj is the sum of the length of that segment, you know, the segment from the value taken at I down to the minimum between I and j, plus the length of that segment where you go from the minimum and then up to the value taken at j. Okay. So a way to write it concisely is Cn of I plus Cn of j minus twice the minimum value, so I want to denote it by Ch and Ij, where this is the minimum of Cnk for k between I and j. Okay? So, you know, Cni minus Cnch of Ij is the length of the green path, and Cnj minus Cnch of Ij is the length of the blue path. Okay? And moreover, Vi min Vj, so the most recent common ancestor to Vi and Vj, is also equal to Vk whenever well, k achieves this minimum. Okay? Any time between I and j that achieves the minimum of the contour process between I and j is actually a time when you visit the most recent common ancestor. Okay? And starting from there, you can see that this is a very somehow robust formula. Okay, so in this way, let's say we can view the metric space V of Tn equipped with the graph distance on Tn. Well, as 0, 1, 2, up to 2n. So I didn't give a name to that, so let's call that dCn of ij. Okay, so if you like, I've encoded the tree Tn in this set of integer and equipped this set of integer with this distance. So it's not quite a distance, of course, because as I said before, there are some i's, there are some points, some vertices which are coded by several integers. Okay, for instance, this point here is visited 4 times. And therefore, this time, and that time, are at dCn distance 0. Okay, so if you like, it's a pseudometric space. Where pseudometric means that you satisfy the same properties as a distance, except that you do not separate points. Okay, and if you like, this is this space in which you identify points which are at distance 0. Okay, so if you like, this is the equivalence relation where I is equivalent to j if and only if dCn of ij is equal to 0. Okay. So it might look like a complicated, it might look like I've made things more complicated, but the thing now is that, the trees that I consider are maps, okay? So they are, if you like, defined up to isomorphisms. And now what I've done is I've given them a representation in terms of a fixed set, okay, which is the discrete interval between 0 and 2n. And this is, much easier to pass to the limit or to do limit theorems in this context. Okay. So let us be more specific. So let's now take scaling limits. So define a rescale distance so let's call it dn of st. So if you like, I want to take this discrete interval from 0 to 2n and put it back, rescale it into 0, 1. So what I want to do is consider the distance in Cn between 2ns integer parts and, well, actually, maybe 2ns and 2nt. Let me forget the integer parts here. In fact, this function can really be defined on the whole interval from 0 to 2n because I define the contour process everywhere. Okay, so this formula makes sense everywhere. Okay, so note. A function on 0 up to 2n squared. Okay, so I want to consider the distance between 2ns and 2nt, and the order of magnitude of this quantity when n is big is the same as the order of magnitude of Cni. Okay, and we know that this is of order square root 2n. This is what I erased just before, so I want to rescale things in this way. Okay. And a corollary of the previous theorem is that dn converges in distribution as n goes to infinity to a limiting function that I want to call dE of st. So that's in distribution in now the set of functions with 2 parameters, s and t, where dE of st is given by E of s plus E of t minus twice the minimum of E between times S and T. Okay, so again, E check ST is equal to the mean of E on this interval between S and T. And moreover, DE is a pseudometric on 0, 1. Okay, there is really nothing special to the fact that E appears in this formula. In fact, if you take any function which is non-negative on 0, 1, and that is equal to 0 at times 0 and 1, this formula, replacing E by this function f, will also give you a pseudometric on 0, 1, and you want to interpret that at the distance of a tree coded by the function in question. Okay? But I'll come back to that later. But the fact is that so the proof here is really trivial. Okay, so this convergence here, directly comes from the fact that that Cn. So let me call Cn the rescaled process. So C2n divided by square root 2n converges in law, well, in distribution uniformly to E. So this first convergence is just a consequence of the formula. Okay, so it implies that if you like, Cn check of these two variables converges to E check of the two variables in C of 0, 1 squared with the uniform norm. And this implies the convergence of this Dn. It's, if you like, it's an application of the continuous mapping theorem. You, starting from a continuous function f, you associate this pseudo distance df, and that's a continuous function from C01 to C01 squared. Okay? And the fact that, well, we could of course check directly that dE is a pseudo distance, pseudometric. In fact, the only difficult thing to check is the triangle inequality, but we also get it, for free from the fact that Dn itself satisfies the triangle inequality. Okay, so since we know that dE is the limit of a uniform limit, if you like, of a even pointwise limit of a function that satisfies the triangle inequality, well, it has to satisfy the triangle inequality as well. Okay, so where are we now? So we know that from a discrete tree we can associate its contour process. And we have seen that when rescaled properly, it converges to the normalized Brownian excursion. Okay? And now what I've done is I've put a distance on the interval 0, 1 using the Brownian excursion. So, by the way, what is this distance? It's the exact analog of the picture that I've drawn over there. So the distance between S and T is just the length of the green segment from the value of E at time S down to the minimum between S and T, and then the length of the blue segment up from that minimum to the value taken at T. Okay. So dE of st is equal to this plus that. Right. Okay. And now what I want to say is that this distance actually codes a kind of a limiting tree. Okay. So in order to do that, let me define the tree coded by E in the following way. So let TE be the quotient set of 0, 1 by the equivalent relation given by points. You know, points are equivalent if they are dE distance 0. Okay. Then TE equipped with the distance dE is a compact metric space. It's called the Brownian CRT. So the Brownian continuum random tree. Which has been introduced in the early 90s by Aldous. Okay, so again, here you see that TE is really parameterized by the interval 0, 1. That does not give a true metric space, so I just want to quotient points that are identified together. And the resulting, I mean, of course, there is a little abuse of notation. dE is really a function on 0, 1, but it does not depend on the representatives that you choose. Okay, so it does define a function on T, and this has to be a distance because you've identified all the points which were at distance 0. Okay, so what remains are points that are separated from each other. Okay. And if you want to think about this equivalence relation, so points that are at distance 0 are points for which, well, the length of both these intervals, the green and the blue here, are 0. Okay, and that can happen only if the points again are facing each other below the graph of E. Okay, so again, somehow you obtain this tree by taking the graph of this function and gluing. You imagine that the graph of this function is a strip of paper. Okay, and you glue together the points that are facing each other below this strip of paper. Okay, and the thing is, in order to do that, you will need an infinite quantity of glue, because this strip of paper is a path of Brownian excursion, and in particular, it has infinite variation. Okay, so you will never be completely done in doing this gluing. Okay, if you try to do it in real life, but mathematically that's possible. Okay, so an important property of T. So okay, I didn't actually prove that it's compact. So compactness comes from the fact that when you have a quotient, when you have an equivalence relation, and take a quotient set, you have a natural projection. Okay, so the canonical projection is continuous. So from again 0, 1 to TEDE. And that's fairly easy to see, indeed. Let's look at the distance between the projection of S and the projection of T. So by definition, it's nothing but dE of ST. Okay, and that's E of S. Okay, I'm writing again, maybe minus E check ST plus E of t minus E check st. And now you see that, therefore, this has to be less than the modulus of continuity of E in the interval between S and T. Okay, because this E check of st, you can write it as EU for U between S and T. Okay, so therefore this is certainly less than twice the modulus of continuity of E taken at the value S minus T. Okay, so this by definition is the soup of E U minus E U prime for U minus U prime less than T minus S. Okay? And since E is a continuous process, you even know better than that. You know that the modulus of continuity of a Brownian motion. Brownian motion is almost 1/2 Hölder path, so you even know at what speed this converges to 0 as S goes to T, for instance. Okay? So therefore, TE is compact as the continuous image of a compact set. Now, what's maybe more important is that TE is indeed a tree. Okay? However, it's now not a combinatorial tree. It's not, if you like, a plain tree in the sense that I've given before, because somehow the set of its vertices now is the whole interval 0, 1. Okay? So the vertices and the edges, they really do not make sense in this context. However, so proposition TE is a real tree, or an R tree. Well, okay, maybe I should have given a definition before. So where I call TD, so that's a metric space, is an R tree if and only if I have two properties. So the first property is that it's connected, but in a strong way. So for every x and y in T, I can connect x and y by a path, but which is also a geodesic path. I want this path to be the isometric image of a real segment. Okay, and that's actually where the R comes from. So there exists phi from 0 dxy to T, which is an isometric embedding such that phi of 0 is equal to x and phi, the endpoint, is equal to y. Okay? And we call phi a geodesic path. Okay? And the second property, well, a tree in graph theoretical sense is a connected graph without cycles. So here I want to forbid the existence of cycles. So there exists no function f from S1 to T that is continuous and injective. Okay, where S1 is just the unit circle of R2, say. Right, that doesn't really matter. Okay? So if you want to think about what an R tree looks like, well, let's take 2 points in an R tree. So we know that they are joined by a geodesic, which is an isometric embedding. It's isometric to a real segment. So I should draw it really as a straight line, if you like. Now let's take a third point. Well, then again, there is a straight line that connects this point to either of those points, but also there shouldn't be cycles, okay? So that means that this straight line, it has to branch on the tree at some point, okay, and form a picture like this. Sorry, it has to branch on the first segment at some point and form a picture like this. And here you should keep in mind that, of course, the geodesic from that point to that point is not a straight line in R2, but we should really think of the distance between that point and that point as the length, the sum of the length of these two segments. It's really the intrinsic, I mean, when I draw a picture of an R3, you should really think of the intrinsic distance between pairs of points, okay? And then you continue, you glue, pieces of real segments in such a way that you form an object that has no cycles, okay? And you can glue infinitely many of them, okay? The set of points where you glue points can be everywhere dense in the, well. Okay, so I'm not going to prove this result. This would take too much time. But as an exercise, maybe. So try. Well, give. Okay, so maybe show that the geodesic from the point coded by t, say to the point coded by 0 in the tree, is given by the following formula. So let's say phi r. So this will be for r between 0 and the distance between 0 and s, and the distance between 0 and s, it's nothing but es. Okay. Sorry, that's t. I have the time t, and well, if you follow what we've done before, so the length of the geodesic is given by the altitude, if you like, of t. Okay, but if you want to actually give a formula for the geodesic, then this should be the projection of, let's say, the supremum of s less than t, such that E of s is equal to E of t minus r. And this is also equal to the infimum of times bigger than t, such that E of s is equal to E of t minus r. So on a picture here, maybe let's make a slightly more complicated picture. So it means that for every r between 0 and E of t, you look at the first time, the last time before t and the first time after t where you attain this level. Okay, so that will give you 2 points. Okay, then you project these points, which are points of 0, 1. Okay, you project them on the tree, and when you vary r, this will give you a collection of points. Okay, which are actually the records on the left of t and on the right of t. Okay, and these are actually the geodesic paths in the tree. Okay, so that's a good exercise to see if you've to start mastering this coding of the tree by intervals. Okay, so time is running short, so Right, so, so I probably won't have time to finish this today, but now, okay, we have this convergence result for the pseudo distance that codes the discrete tree on 0 to n. The problem is that and it converges to the pseudo distance coding the Brownian CRT. Okay, and one issue with this result is that it depends. It seems to depend very much on the way that I've encoded the trees. Okay, so it's much better, at least for the mind, to have a context in which the convergence holds not at the level of the coding processes but the trees themselves. Okay, and so we can turn the convergence result of dn to dE into a convergence of the trees themselves when seen as metric spaces. And a way to do that is to use the so-called Gromov-Hausdorff topology. So actually the Gromov-Hausdorff metric. So the Gromov-Hausdorff metric is a way to measure how far apart two compact metric spaces can be. Okay? So let's take two metric spaces XD. So let XD, X prime, D prime be compact metric spaces. And let's imagine I want to compare them. So one way to do that is to first try to pair the points of the two spaces together. And one way to do that is to use a so-called correspondence. So we call R a subset of X times X prime, the product space, a correspondence. So between X and Y, X and X prime. So if, well, for every X in X, there exists an X prime in X prime, which is in correspondence. Okay, and vice versa. So every point of either of these two spaces is in correspondence with at least one point in the other space. So for instance, X can be in correspondence with 2 points or even more than that. Okay, and vice versa. The point on the other side is in correspondence with a point in X. And the distortion of R is defined by the following formula. So you take 2 points X, X prime in correspondence. You take 2 points Y, Y prime in correspondence. And take the distance between X, Y minus the distance prime between X prime and Y prime. And you maximize over all these possible pairs. Okay? So it means that you compare, if you like, the distances between these pairs and points with their analogues upstairs. Okay. Now, if you try to find, so you will see that somehow the distortion of R will be small when distances in X look very much like the distances in X prime, okay? At least with respect to this way of pairing the points together. Okay? And it turns out that if you minimize now the distortion over all correspondences, then you obtain a number, and this number defines a distance. Okay, so let me finish with that. So theorem, well, definition theorem. So let dgh of xd and x prime d prime be the infimum over all correspondence between x and x prime of the distortion of R. And usually there is a convention that you divide by 2 for reasons that I don't have time to explain now. Then DGH is a metric, well, let's say a distance on the set of compact metric spaces viewed up to isometry. Okay? Obviously, if I have two metric spaces which are isometric, I can build the correspondence between these 2 points, between these two spaces by, well, fixing an isometry and letting x be in correspondence with its image by the isometry. And in that case, it's easy to see that the distortion of this correspondence is 0. Okay, so in this case, this infimum is in fact equal to 0. Okay, so certainly two isometric compact metric spaces are not distinguished by this DGH. Okay, so when you view metric spaces up to isometry, this is indeed a distance, and moreover, so let me call this set M. We call that next time. And moreover, DGH is complete and separable. So it seems like it's defined on the huge space, but in fact it's not really. When you view compact metric spaces up to isometry, this is a very reasonable space, and in fact it's separable. In fact, finite spaces with, say, rational distances are dense. Okay, so so this is this distance has been introduced by Gromov in the context of studying, almost Riemannian metrics. Well, actually, he introduced it in several contexts. He also introduced it in asymptotic study of groups, and it's a very powerful tool in geometry. And we'll see next time that with this distance, the rescaled uniform random trees here actually converge to the Brownian CRT. Okay, and that will serve as a first step to prove the convergence of uniform quadrangulations. And that's all for today. Thank you. Any questions? Okay, coffee break.
No?
No? Oh, sorry. So, okay.